Hello, my fellow mathematician. Welcome to the study of ordinary differential equation. Today we are looking at the linear differential equation with constant coefficient. Linear differential equation of under n is an equation that can be written in the form which I have shown here. A naught of x d power ny over dxn plus a power 1x dy power n minus 1 divided by x power n minus 1 plus a2 function of x d power n minus 2 y divided by d x power n minus 2 plus all the way to the last term, which is a n of x y, which is function r. So we call this equation 1, where a function of x is equal to a naught, a1, a2, a3, all the way to an are functions of x strictly. They are functions of x strictly or constant. So a naught, a1, a2, a3, all the way to an are functions of x strictly or constant. Now, there are three possible cases for our differential equation 1. This is the general differential equation of under n. Now, there are three possible cases which we are going to study. Case number 1, it is when r of x is equal to 0. So when r of x, that is the part on the left hand side of, so when that part is equal to 0, then it means that this equation here, it means our equation, this one, is a linear and homogeneous equation. In the case if Rx is not equal to 0, then this equation is linear but non-homogeneous. If Rx is not equal to 0, it implies that this equation here, it is linear but non-homogeneous. On how to study on how to solve ordinary differential equation which are homogeneous, you can check in my channel. I've already done it for us. Now, if r is equal to 0, if r of x is equal to 0, then equation 1 is homogeneous when all the values of y are of the same degree and its derivative. So those are the three possible cases whereby r is equal to 0. We have this equation being homogeneous. Where r is not equal to 0, the equation is linear and non-homogeneous. And where r is equal to 0, and then all the functions of y are of the same degree and its derivative, then the equation is homogeneous. So this equation can be linear and homogeneous, linear and homogeneous, and homogeneous, depending on the value of Rx. Now, the next thing we want to consider is the second order linear difference equation with constant coefficient, with what is called constant coefficient. Now, this equation is given by the following. This is a second order linear difference equation, which is given by this a1, second derivative of y with respect to x, plus a2, first derivative of y with respect to x, plus a3y, which is equal to rx. We label this as our equation 2. Now, in this case, a1, a2, a3 are all constant. Now, in case rx on the right hand side of this equation 2 is equal to 0, then this equation 2 here will become linear and homogeneous. It becomes linear and homogeneous, and it takes this form: a1, second derivative of y with respect to x, plus a2, first derivative of y with respect to x, plus a3 of y is equal to 0. Now, equation 2 or 3, this is equation 3. Our equation 2 is this one here. This equation here is our equation 2. So our equation 2 or 3 have two essential arbitrary constant. They have two essential arbitrary constant, since they are of the second order in their general solution. So the general solution of this equation here, because it is of the second order, it will have two essential arbitrary constants when we obtain its general solution. So it is important you note that. So if y1 and y2 are two independent solutions of equation 2, which you have shown you above, then any linear combination of C1, Y1 plus C2, Y2, where C1 and C2 are all constant, is also a solution of the differential equation 2. So what you want to do here, it is to prove that that is true. So we let the left-hand side of equation 2 to be equal to 0, that is r of x is equal to 0, so that now equation 2 becomes linear and homogeneous. Also, we let y1 and y2 be two independent solutions of this equation here. A1, second derivative of y with respect to x, plus A2, first derivative of y with respect to x, plus A3y, which is equal to 0. Here, remember A1, A2, A3 are all constant. Then we substitute y1 and y2 separately into the difference equation 1 above. We are going to have, so where you have y, general y, we substitute it with y1, that is number 1. Then number 2, where you have y, you substitute it with y2 to obtain the following. So after you have substituted y1, you are going to obtain this a, second derivative of y1 with respect to x, plus a2, first derivative of y1 with respect to x, plus a3, y1 is equal to 0. You call this equation 2. Then for y, when you substitute your y2, you are going to get a1, second derivative of y2 with respect to x, plus a2, first derivative of y2 with respect to x, plus a3, y2 is equal to 0. That is, now you call this equation 3. Now, if y is equal to c1, y1 plus c2, y2 is also a solution, then it must imply that when you substitute the value of y in, that is now your y as c1, y1 plus c2, y2 in equation 1 above, here, when you substitute the value of y here as c1, y1 plus c2, y2, it means also that one will be a solution of this equation. So the next thing we are going to substitute, instead of y, we substitute it with c1, y1 plus c2, y2 as shown below here. So a1, second derivative of y with respect to x. Our value of y now here, this one is this part here. First derivative of y with respect to x, our y is this part here, c1, y1 plus c2, y2 plus a3 bracket c1, c2, y2, close time bracket is equal to 0. That is equal to 0. Now, we remove the bracket and we collect the values with y1 and c1 together to obtain this c1, a1, second derivative of y1 with respect to x, plus c1, a2, first derivative of y1 with respect to x, plus c1, a3, y1. Then, plus c2, a1, second derivative of y2 with respect to x, plus c2, a2, first derivative of y2 with respect to x, plus c3, a3, y2 is equal to 0. Then, in this first 3, here, you can see c1 is common and it is constant. We factor it out to obtain the following. And also in this other case here, the last 3 terms, here we factor c2 because it is common to obtain the following. So factoring c1, we are going to be left with the a1, second derivative of y1 with respect to x, plus a2, first derivative of y1 with respect to x plus a3 multiplied by y1. You close the bracket plus c2, which we have factored into bracket a1 second derivative of y2 with respect to x plus a2 first derivative of y2 with respect to x plus a3 y2. This is equal to 0, which is equal to 0. Now, going back to equation, so this part here from equation Roman 2 and Roman, this part is equal to 0 and this other one is equal to 0. When we check what we have up here, you can see from Roman 2, this is equal to 0 and this other one is equal to 0. So all this part here is equal to 0 and all this other part is equal to 0, meaning that it is true that any linear combination of C1 y1 plus C2 y2 is also a solution of the differential equation 2, provided y1 and y2 are independent and provided C1 and C2 are constant. So thanks so much for taking time to study linear differential equation with the constant coefficient with me. This is the general overview. What we are going to do now, we are going to consider different cases in subsequent presentation and to give some examples for us so that we bring this concept home. If you have not yet subscribed to my channel, remember to do so that you don't miss a single video which I upload for us every day. Bye-bye. See you in the next presentation. Remember also to click on the notification bell so that whenever I post a presentation, you are going to learn together with us. Bye-bye.